Good morning guys and welcome back to Dynamics course. In this video lecture we're going to start chapter 70, which is the last part of this course, and this chapter will cover the kinetics of a rigid body. So in the previous chapter, chapter 16, we covered the kinematics of a rigid body, and we saw how to derive the acceleration and the velocity using the motion analysis, how to find the instantaneous center of zero velocity, and it was all related to kinematics. And as we saw in the beginning of this course, the kinematics of a particle is in fact related to the velocity and the acceleration of this particle. And then we talked about the causes behind kinematics, which is in other terms the kinetics of this particle, and this is related of course to the forces causing the motion and causing the variation of velocity or causing the acceleration of this particle. Now this is also applied to the rigid body. So we started in the previous chapter on the kinematics of a rigid body, and then in this chapter we're going to talk about kinetics of rigid body, which is related to the forces exerted on this rigid body. But before going to the forces, I'm going to start by the mass moment of inertia. And guys, I have derived the area moment of inertia in details in statics, so you can go and watch the videos in the link shown in the description of this video, where you can find out how to derive the area moment of inertia and how to find the equation for different shapes and different forms. Now here, I'm not gonna talk in details about the mass moment of inertia. I'm gonna talk briefly, but I want to introduce it by doing an analogy. So guys, I think this is the best way to understand what is the mass moment of inertia physically. If I take the Newton's second law for the translational motion, I know that the sum of forces is equal to ma. And this means that m, the mass, is equal to the sum of forces over a, which means m is the resistance to do a translation. So if m increases, I need bigger forces to attribute to this translation. Now, if I do the analogy between translational motion and rotational motion that we're going to talk about later on in this chapter, you can see, guys, that the sum of moment is equal to I times alpha, where alpha is the angular acceleration. I is what is called the mass moment of inertia. If I do the analogy, I is similar to m. Since m is the resistance to do a translational motion, I, in fact, is the object's resistance to rotation. So this is what is the mass moment of inertia physically. The mass moment of inertia is a measure of an object's resistance to rotation. And analytically, I is given using this integration. I is equal to the integration of r squared dm over the whole mass. What is r? R is the distance between this dm and the axis about which I need to find the mass moment of inertia. Which means, guys, if I change this axis, this mass moment of inertia will, of course, differs. Thus, the value of I, the value of the mass moment of inertia, differs for each axis about which it is computed. Now, if I substitute the m by rho dv, this will be much easier to compute the integration. Why? Because in fact dv will be related to the dimensions, and I'm doing the integration of r squared, which is a dimension. All right, and in most cases rho is constant. So if rho is constant, I can remove it from integration and then do the integration of r squared dv. Now, I want you guys to memorize some commonly used mass moment of inertia. Why? Because, in fact, in some cases, I used this mass moment of inertia to find out what is the mass moment of inertia of much a bigger, larger shape, which means I can use this thin circular disk as my differential element being integrated over the entire body to find the mass moment of inertia. And I'm gonna use it, in fact, in this lecture. And this is also applied to the thin plate. So I want you guys to memorize the mass moment of inertia of the thin circular disk as well as for the thin plate. And I'm gonna take one case, which is here IZZ have R squared, and I'm gonna prove it in this slide. So let's prove this mass moment of inertia. So this mass moment of inertia around z-axis, as I said, the mass moment of inertia is related to the axis about which it's computed. So here I'm gonna find IZZ, which is the mass moment of inertia of this thin circular disk around z-axis. But before doing this, guys, I want you to find what is the mass of this thin circular disk. I know that the mass is equal to rho times the volume, which means it's equal rho times the volume of this thin circular disk. Now, what is the volume of this thin circular disk? It's in fact the area, which is pi r squared, times the thickness, which is here t, a small thickness called t. So this is the mass. I'm gonna put it aside because in fact I'm gonna use it later on. Alright? Now, as I said, what is IZZ? By definition, the mass moment of inertia around this axis is equal to the integration of r squared dm. And I'm gonna directly replace the m by rho dv. Rho is constant, so it could be removed from integration. Now, this integration is over v. In fact, it's over m, but since rho is constant, so I can remove rho from integration and do it over the volume v. Now, let's replace dv by its value or its equation. What is dv here? In order, in fact, to find IZZ of this thin circular disk, so in order to find the mass moment of inertia of this thin circular disk around Z, I'm gonna take a differential element, right? So this differential element must have a distance away from Z, right? So I'm gonna take this differential element, which is a ring. All right, so guys, if I take, in fact, the top view of this thin circular plate, the thickness of this ring will be, of course, dr, and the distance between G, which is the axis ZZ, and this ring will be small r. Alright, so r here is variable, alright, and this r is moving from 0 to the radius of the whole thin circular disk. So let's, guys, call this radius, the whole radius, big R, so that we can differentiate between the variable r going from 0 till big R, alright? So the mass of the whole thin circular disk is rho pi big R squared t. Okay, so if I want to do this, then the integration will be r squared. So I'm going to remove rho from the integration. dv, and what is dv? dv is the area of this ring times t. Now, what is the area of this ring? If I open this ring, if I open it, guys, because it is thin, then this will be as if it is a rectangle. Now, what is the area of this rectangle? It's this length times this thickness. Now, or this width. This width is what? It's dr. And this length is, in fact, 2 pi r. Alright? So it is rho, the integration of r squared, 2 pi r dr. And now the integration will be over r, where r is going from 0 till big R. And then r squared times r will be r3. So if I do the integration, this will give me rho times 2 pi times r 4 over 4. And here I forgot the thickness T, because it's in fact the area times the thickness. This is dV. Alright, so times T. Now 2 over 4 is 2, and if I take rho pi r squared and not 4t, remember what is this? This is m, and this means, guys, that this will be m. r4 over r squared is r2 over 2. Alright? Which means, guys, that izz here is equal to half mr squared. Now, how can I find iz prime z prime? What is z prime z prime? It is an axis at the edge of this thin circular disk, but it's parallel to zz. How can I find the mass moment of inertia around zz prime? This is in fact by applying the parallel axis theorem. So if you go back to statics, you can remember this because we used the parallel axis theorem in the area moment of inertia. It is the same. You can find out the derivation here, or you can directly go to the equation. If you remember, it was I is equal to Ig, which is the mass, the area moment of inertia around the axis passing through the center of mass or the center of area, plus AD squared, area times d squared. Now here since I have to find the mass moment of inertia, it will be I is equal to Ig, which is the mass moment of inertia around the center of mass, plus m, the mass, times d squared. M is the mass of the body, and d is the perpendicular distance between the parallel axes. All right, so if I apply this here to my equation, izz prime is equal to izz that I found earlier, so it's mr squared over 2, plus the mass times the distance between these two parallel axes, and this distance here is r, so it's a squared, right? So mr squared over 2 plus mr squared, this will give me in fact 3 over 2 mr squared. All right, so guys, this is how you can find the mass moment of inertia. It's by integration to find it about an axis passing through the center of mass, or by using this integration and adding to it mr squared by using the parallel axis theorem. All right, guys? Now, in some problems, they can give me what is called the radius of gyration. Now, what is the radius of gyration? I know, guys, that I is equal to what? I is equal to the integration of r squared dm. Now, if I assume that r does not depend on dm, or that dm doesn't depend on r, then this will be, of course, r squared times m, the total mass, all right? Okay, so as if there is what is called a radius of gyration, k, where I is equal to k squared times m. So I can give you this k, or it will be given in some problems, and then you can find I directly by doing the multiplication of k squared times m, and this is what is called the radius of gyration, and it has, of course, the equation of radical I over m. So either I can give you this k so that you can find I directly as k squared times m, or after you do the integration to find I can ask you to find the radius of gyration, which is by doing the radical of the I, the mass moment of inertia that you found from integration, over the mass of this body.